In this course, so far, we have discussed all numerical schemes based on uniform grids. Uniform grids are simple to generate, but for most practical applications, uniform grids are extremely expensive. Creating uniform grids in a large domain requires very large number of grids, and that increases the amount of calculations to a great extent. In many practical cases, such huge calculations are unnecessary. And in practice, uniform grids are exception. Non-uniform grids are most common in safety. However, when we use non-uniform grids, it has certain difficulties. First, of course, creating non-uniform grids involve little more calculation than uniform grids. But that is only first part of the problem. The second problem is that whenever we create non-uniform grid, the accuracy of most numerical schemes will reduce. When we say certain numerical scheme is second order accurate or third order accurate, what we mean is that if we apply that scheme in an uniform grid, it will be second order accurate. So for instance, if you are using central difference derivative in a non-uniform grid and you are claiming that it is second order accurate, you are probably not entirely right. You have to give sufficient information about your grid so that the audience can understand that your scheme is indeed second order accurate. In fact, it will never be exactly second order accurate. It will be close to second order accurate. And that is something we'll discuss in this lecture. Once again, consider our function ux in certain arbitrary interval a, b. If the grid is uniform, then xi plus 1 minus xi equals delta xi, which is a constant irrespective of I. While if the grid is non-uniform, then at least for one I, this delta xi is not equal to delta xi minus 1. Now, if you try to find derivative in a non-uniform grid, you will find that the forward difference will be very simply given by ui plus 1 minus ui divided by delta xi. Here we are taking xi plus 1 minus xi equals delta xi. So you will take that as delta xi or you will denote that as delta xi plus 1. That is your choice. But the distance between xi plus 1 minus xi will come in ui prime forward difference. Similarly, in backward difference, we have ui prime equals ui minus ui minus 1 divided by delta x I minus 1. That is the distance between xi and xi minus 1. The schemes are first order accurate. The forward difference is of the accuracy of delta xi and the backward difference is of the accuracy of delta xi minus 1. Of course, I haven't proved this, but you can prove this forward and backward difference expressions using Taylor series expansion. However, the forward difference, backward difference scheme remains first order accurate no matter we are taking uniform or non-uniform grid. But will it be so for all cases? Let's see. Let's take a case of central difference. In central difference, we find u prime based on ui plus 1, ui minus 1. So let us first have the Taylor series expansion of ui plus 1, that is ui plus delta xi ui prime plus delta xi square by 2 ui double prime delta xi cube by 6 ui triple prime, etc. And ui minus 1 is ui minus delta xi minus 1 ui prime plus delta xi minus 1 whole square by 2 ui double prime, etc. So if I take ui plus 1 minus ui minus 1, both ui cancels out, and then we have delta xi plus delta xi plus 1 ui prime plus delta xi whole square minus delta xi minus 1 whole square by 2 ui double prime plus delta xi cube plus delta xi minus 1 cube by 6 ui triple prime, etc. So we can write ui prime equals ui plus 1 minus ui minus 1 divided by delta xi plus delta xi minus 1. And this is fine. This part is exactly like the central difference in uniform grid. And then there are additional term that are truncation errors, and truncation errors involve delta xi minus delta xi minus 1 by 2 ui double prime and delta xi square plus delta xi minus 1 square minus delta xi minus 1 divided by 6 ui triple prime. So we can write ui prime equals ui plus 1 minus ui minus 1 divided by delta xi plus delta xi minus 1. This part is exactly same as what we get in uniform grid, plus the order of delta xi minus delta xi minus 1 and delta xi square plus delta xi minus 1 square minus delta xi minus 1. Now you must be wondering that why we are keeping both the terms in the order. Only the first one should be sufficient, but that is not, and we'll see that right now. You can see within the order term there are two terms, and depending upon the nature of your grid, one of them can dominate. For instance, let's assume that delta xi and delta xi minus 1 are almost equal. They are very close to each other. In that case, the first term within the order will be very small and may be dropped. So you can assume that delta xi equals delta xi minus 1. Then the first term is 0. And the second term, if delta xi and delta xi minus 1 are equal, then in the second term, only delta xi square will remain. That means the entire scheme will be second order accurate. On the contrary, if let's say delta xi is much higher than delta xi minus 1, then what happens? Then you can think of that, well, if delta xi is much larger than delta xi minus 1, we can have this delta xi minus delta xi minus 1 is almost equal to delta xi. That makes the scheme only first order accurate. To understand this, you can just set delta xi minus 1 to be 0. Then what happens? The first part of the order becomes delta xi, and the second term in the order becomes delta xi square. That means the order of accuracy becomes delta xi. Then the scheme becomes first order accurate. Exactly same argument we can put if delta xi is much smaller than delta xi minus 1. Overall, it means that if delta xi and I minus 1 are very close to each other, then the scheme is almost second order accurate. If delta xi and delta xi minus 1 are not close to each other, then the scheme goes more toward first order accuracy. So in general, the scheme will hover somewhere around the accuracy of 1 and 2. That means first and second order. So you cannot claim that even if you are using a central difference scheme, you cannot claim that your derivative is second order accurate unless you give specific information about your grid. So the accuracy of your scheme depends on the grid if you are using a non-uniform grid. In all practical purpose, if you want to retain high accuracy in a non-uniform grid, the difference between two consecutive grids must be very small. In practice, we never increase consecutive grid more than 10% than the previous one. But that is just a thumb rule. But keep these consecutive grids as close to each other as possible. You will see many times people violate this and get results that are not very accurate. You can follow the procedure that we have described here and find the order of accuracy in a 3-point forward difference derivative and 3-point backward difference derivative, both in non-uniform grids. That's all for this lecture. I'll see you in next class. Thank you.